Today we're going to be looking at traffic signals again, and today we're moving in to how to calculate the total delay that a vehicle, or the average delay a vehicle would experience at a signal, or the total delay that all the vehicles experience at a traffic signal. And then we use that to calculate what the level of service is for signals. And we've talked, I may have mentioned it briefly before, that when we were doing levels of service calculations for freeways and for other roads, that traffic signals, we can calculate the level of service for those themselves, and it's all based off of delay. And it's probably when we were calculating our original delay pieces through there, we talked about that just briefly. If you remember that our capacity of a traffic signal is calculated based on the saturation rate of a single lane or a group of lanes that are all moving the same direction, so all through movements or left turns or something like that, all in the same cycle, in the same phase timing for the traffic signal. It's equal to that saturation rate times this ratio over here of the effective green time versus the cycle length. And so that's the percentage of time that movement gets green time through there. And so we just take our saturation rate and multiply it by that ratio, and that gives us what the capacity is for that movement through there. And you can see over here we've got, if we were to program, this is a time-space diagram for a traffic signal, if we were to program this, this is a southbound movement through here, that it gets 60 minutes of green time all the way through, our capacity is going to be the saturation rate through there. If we had an entire hour of green coming all the way through here, so here's our band. This is a traffic signal location here. Here's that band, and we'll see here in a second what it looks like when we have some red phases, but this is all green. And so for an entire hour, traffic just flows right through here, nothing is stopping it, right? So this is, let's say this is, if this is going along Lincoln Way, all right, so this would be one of the signals downtown. Maybe this is the signal out at University, and then another signal on downstream of that. You can see how traffic would flow right through. It never stops, right? So if we were picturing Lincoln Way by campus, this traffic just moves all the time and never has to stop because this light never turns red, right? In an actuated signal, this happens late at night. You can get a full hour of green on there because if there's nobody on the side road, the signal will never switch over and turn red for the main line and green for the side road unless there is a car there. So you do get some really long periods late at night. Now you're not going to get the 1,800 vehicles in an hour going through there late at night because there's not that many people out there, but they could have if they all wanted to drive then. You could have had that much green time through there. So that's what this is looking at. Each of these points here where these bands are would be a different traffic signal through that. If we now look at these green bands, this is what we call this in this time-space diagram. So this scale down here is this is our time, and this scale over here is distance. And so this is, maybe this is a quarter mile between two traffic signals, and then this is, an eighth of a mile on to the next one, something shorter, obviously, because they're closer together, right? And what we'd like to do in traffic signal design is if we release a bunch of cars, these are all, let's say, headed southbound, if we release all these cars when this light turns green up here for that movement, and we'll call this the southbound movements, right? So the southbound through, so they get the green light here. All these cars come this direction, right? So they're moving a certain distance over a certain amount of time. Right? So that's our time-space diagram. And when they get to this next light, we've done a really good job of timing it, and they magically get green right when they get there. And then they pass on through. And the third light in this series also magically gives them a green right when they get there. Right, so we call that a green band, and sometimes we call bandwidth. How many vehicles can you get through in that green band? If you group a bunch of vehicles together, we call it a platoon, and so this platoon is rolling through, and they never have to stop. Right, so you've done a perfect job as a traffic engineer, and you have perfectly timed those lights, and these cars never have to stop. All right, now can you do this in real life? Yes. It's hard. It is hard. And it's a lot easier. In fact, the only cases where it really works is when you've got a one-way road. And so this, if there is no northbound, everybody's just going southbound, yes, you can time these, and we've been doing that since the 60s, even using old electromechanical controllers. We were able to do a nice job of keeping traffic moving through on a one-way road. And that's one reason some cities would split their two-way roads into one-way pairs. One road's going north, let's say, and then a block over, there's a road going south only. And then you could time these lights perfectly through there at a certain speed, as long as people maintain that speed. And the slope of this line would be your speed in here. So as long as you maintain that speed, you'll make the green light on every one. So we've retimed this now, and we've got this red phase, and then it switches back to green and red. So we're about a third of the time now we've programmed this to be green, and so our capacity has dropped, right? And so now it's our saturation rate times 33% of the cycle length, and so we've got 1/3 the capacity we did before. All right, so that would be a pretty simple example, and you can visualize it now. These would be trajectories of vehicles as they come through. And again, we've got this perfect time-space diagram, and everyone's moving through and never have to stop. Right, so now we're going to look at this is some real-world data from that. So here is, and these are actually moving north this time, going this direction. You can see here's our green bands. Well, these two lights at two different intersections are starting their green right at the exact same time. Well, the light turns green, takes people a few minutes to get started up, and we talked about that lost time at the beginning, right? So this is capital G. Sorry. This is capital G. That's when the green time starts, but the effective green, remember, is about 2 seconds after that. And then this platoon would move through. These dark lines are the trajectories of individual vehicles. So they start here, they're waiting on red, the light turns green, they start moving north. They get through this next light, but it's getting toward the end of the cycle because these two lights actually start at the exact same time. Luckily, this one has a longer green time. So those cars get through, they get to this next intersection, and the light's red, and they just missed it. This guy snuck through. He's bad. So he busted through on the red. Everybody else was following the law, and they stopped and waited until the light turns green, and then they go on ahead. Then they get through on the next green phase. And you can see this guy, even though he snuck through here, he still had to wait at the next light. He's not that much far ahead of him. So see, it doesn't pay to cheat. So, and then you can see here's some vehicle trajectories here that started, probably turned on, probably right turn movements or something, or from the side road and so they started at different times. They all come up here, they all get caught by this intersection on red, right through there. They wait, and then they all move forward. Here's some people sneaking through on the red again, not good. Through there, they all have to wait up here, and then they move again, and some don't get through. So here we can see where you've got some spillback. Not everybody made it through this light and got on this green band. Some got stuck, and some snuck through the end, and then others had to wait. Right, they were here, they thought they were going to get through, but that queue was so long, they got stuck and they had to wait, and then they got through later. Do that. So this is what time-space diagram would look like, and I'll try to post a real time-space diagram from a location on the website coming up here. All right, so digging a little deeper into that graph, we can see, like with this one piece here we looked at a minute ago, these people were kind of starting whenever, and it's kind of a wide spacing, right? So they're turning in from other driveways. They're doing right turns on red from the intersection downstream or upstream, I guess it is, of that. And so it's kind of a random arrival. Well, then once they're past that, then when they departed, they're all bunched up together, right? And so this one they were loosely spaced and quite widely spaced on their arrivals. They all get bunched up into a queue waiting for the red light. When their light turns green, they all move forward at basically the same time. Now you're probably your saturation flow rate, right? So they're all bunched up together, so you get these lines are very close together, which means that there's not much space between the cars as they move forward then. All right, so it's a much higher rate through that. And so you can see our arrival rate in this case was lower than what our departure rate was. So our arrival rate was pretty gentle. However you want to count however many trajectories there are in air over that amount of time, that's the arrival rate. Well, when they leave, they're leaving at a much denser rate. And this is pretty common, right? Because we've bunched all the cars together, we've packed them into a platoon, and now that platoon moves forward together through that. And we can go back to calculating delay. If you remember, we did this before spring break. We can look at each delay at a traffic signal as well through there. And down here, this is from the textbook, so it's in black and white. We've got the red band here, which is this black part, and then we've got a green band, and the red band, and green band, just like we were seeing in that time-space diagram. Right through there. And if we say cars are arriving at exactly the same rate all day long, this is that arrival rate here. So it's just, again, like we did before when we were calculating delay in one of the last chapters, is this arrival rate usually here on top. Cars have to wait during the red, and once it turns green, cars depart. And they're departing at some saturation rate times time, the amount of time they've got there. So we were saying that they can leave at that saturation flow rate because they're all bunched up. And then they'll catch up, and then the queue empties out, and then we still have some green time left. And when people, as they arrive, just blow right on through, and they don't have to stop. And then the light turns red, and now cars that arrive right here have to wait until the light turns green again. Then they can depart again at that saturation flow rate, leaving from the signal through that. The queue clears out. Everybody who arrives during this last phase of green right through here doesn't even have to stop. All right, doesn't even have to wait. And then the light turns red again. They have to wait, and then they depart through there. And that's, again, this is a pretty simplified version with a exactly constant arrival pattern through there. Right. So this is our effective red time. Here's the time that people are leaving, and so that's the amount of flow that gets all of those cars caught up, right? So that's T sub C is the amount of time it takes to clear the queue, and so that's the clearance time through there. Here's our effective green time, a little g, remember, is our effective green time through that, and this is the cycle length out of there, right? So we could handle more cars here. We've got some time in here where we're not at saturation flow rate through there. This would be the saturation flow rate line. This is obviously less slope, and so it's a less busy time coming through that. So here's some sample problems which you'll get to practice on eventually in the homework through there. So we've got an intersection has a flow rate, saturation flow rate of 1,500 vehicles per hour. Cars are arriving at 800 vehicles per hour, so less than that saturation flow rate, right? And so we've got a pre-timed signal because that's what we can calculate easily through there. We've got a 60-second cycle length. We have DD1 queuing, which you remember from earlier, just means it's deterministic and there's only one lane through that. And they said that, by local standards, you have to set the timing so that that queue dissipates 10 seconds before the end of the effective green portion of the cycle. And so assuming that approach capacity exceeds arrivals, determine the maximum length of effective rev that will satisfy the local conditions. And so this is a different way to look at signal timing, is how do you want to jump in here and time your signal so that you've got 10 seconds that at the end of every cycle that the queue has dissipated before it goes red again. And so how do you balance that red and green time through there? And so if we looked at this one, this is our theoretical departure line. And so that's our departure rate. This is using the terminology from before when we were calculating delay. So here's our departure rate times whatever time it is. And so that slope's there, right? And so what you're going to see is that slope was going to match these departure slopes. There's going through here. Now, and no, in real life, we don't have a perfect triangles like this, right? People start off a little slow, then they pick up speed, and so this would be slightly sloped in here, a little bit rounded, and then it would pick up and finally match that. So we're gonna use the nominal departure rate and assume that since this is effective green and effective red, and not just red and green, that by the time effective green starts, they have come up to speed at the first 2 seconds, and they're moving now at the standard flow rate through there. So and so our arrival rate given to us in that problem is less than that departure rate right, through there. This is the saturated departure rate, 1,500 vehicles per hour. This is the 800 vehicles per hour on the arrival rate coming through there, right? And we want to make sure that this time, this gap right in here is 10 seconds, at least 10 seconds, according to that jurisdiction's rules through there. One thing to note is that all of these rates, these departure rates, are equal. They have the same slope. There's the same rate as that saturated flow rate was, right? So this would be the departure rate if there was a ton of cars, no limited supply of cars, and there was no red lights ever on a signal, which would be odd, right? This is what your maximum theoretical throughput would be, right, through there, which does match then the departure rates after each cycle, right? So when the green hits, until that queue clears out, we're at that saturated flow rate. So we already talked about that a little bit through there. So that's how you'd set that up. That's what it would look like graphically, and then you can calculate, based on that, to set this time gap in here to be 10 seconds, and then you can calculate what your red time would have had to be. So that's how you'd set that problem up through there. This is what a more typical intersection looks like, and so we remember those problems we were doing about coming into the national park and the toll booths. And so for the first 15 minutes, the rate was X. And then after that first 15 minutes, the rate was Y as far as arrivals go. And then what time did the queue clear? Right? That was some of the questions we had in the previous chapter. We were calculating delay and traffic flow. All right, so we can do the same thing with traffic signals. And so here's our cycles. We have a 60-second cycle, which is not that a realistic cycle length unless you had like a T road, but it makes math easy. So we're going to use 60-second cycle lengths, right? So it's 1 minute each cycle. And so here's cycle 1, cycle 2, cycle 3. Again, we're starting off, we're saying that we measure our cycles at the start of red, and then we have the green on that. This is a single movement, a single phase, all right, through here. Then we go back red, then green, red, and green, right, through there. So each one's a cycle through that. And then here's how many vehicles that are getting through, right? And this is time in seconds down here. So again, just set up the same way as we were calculating delay before. So, but now this is our arrival rate, right? And so after the first cycle, the arrival rate changes, and then magically, right, when the cycle changes the next time, the arrival rate changes again. All right, so, okay, normally your arrival rate wouldn't change magically right when the cycle did either, but this is handy. So we're at 60 seconds, we had 15 cars come through. At 120 seconds, we've had 23 cars come through, right? So the rate changed after the first minute. And then at 176 seconds, we've got a portion of cars. So we're doing it by math this time. So we have a fraction in here. And that's where the queue would theoretically, this is a theoretical calculation. That's when the queue would theoretically clear is at 26.8 vehicles. Well, okay, it's kind of hard to clear. 26.8 vehicles would be 27, right, through there. But that's where the math would show you that you would come out in your clearance. So our arrival rates are changing, and this is normal, right? We don't run, typically it's not like this earlier one. We're not going to have this constant arrival for a long period of time. As you already know, we've got that peak hour factor, right, for the peak 15 minutes of the peak hour. And obviously, the only reason we have a peak hour factor is because every 15 minutes, if you measure it in 15-minute bins, you're going to get a different number. You're going to get a different arrival rate. And that's what this is showing, right? So this is maybe right before 8 a.m., then it starts slackening off, and it slacks off even a little bit more, right? So traffic is slowing down on arrival. All right, this is right before class starts. Class started. Now, a few people are late. We still get a number coming in, and then here's the really late people, showing up right through there. So that's that. But our departure rates are the same. So in each case, when that light turns green, everyone's ready to go. Off they go, right? So here's the light turns green, and shoom, off they go. Light turns green, shoom, off we go, and so forth, right? So those departure rates are this rate here, and that's, again, that saturated flow rate as they go through. When the light turns red, no one's moving, so we've got that, right? And if we remember right, this is number of vehicles in the vertical axis, and so that was one of the questions we used to have to answer is how many vehicles are in the queue at a certain time. And again, any point on here, if you drew a vertical line, that's how many cars are in the line, right? Right before the light turns green, you have the maximum number of vehicles in that queue, right? Look at that, right, through there. Then it clears out, but we didn't get everybody through the light, right? Not everybody made it through. That's what this is showing. And so at the start of cycle 3, now we've got the cross hatching going this direction. We've got theoretically 18.88 to 23 vehicles. If you took 23 minus that would tell you how many cars are in that line. So again, this is a theoretical calculation. We aren't actually going to have 0.12 cars waiting somewhere through that. They wait, and then we finally, in the cycle 3, because the rate of arrivals has dropped enough over 3 cycles, we catch up right at this point, 4 seconds before the end of cycle 3. We finally catch up, and the queue is cleared out. Right, so that's what this is showing. And if we added all these shaded areas together, what would that give you? Right, that'd give you the total delay over 3 cycles. Right. So that's vehicle seconds. That would be vehicle seconds of delay. And we could add all those 3 together. That'd be the total vehicle seconds of delay for 176 vehicles through there. Right. So we could calculate that through there. Here's another example problem. So we've got a saturation flow rate of 1,800 vehicles per hour. At the beginning of effective red, there were 6 vehicles already in the queue. And the vehicles arrive at 900 vehicles per hour, so half the saturation rate through there. We've got a 60-second cycle length, 25 seconds of effective red. All right, so most of our time is actually effective green, so that's good. All right, through there. So what's the total vehicle delay after 1 cycle? All right, so assuming DD1. So let's draw this out. Let's work through this problem and see what we can do with it. So we start plotting our graph. So time over here, we're going to do it in seconds. As we measure traffic signal timings are usually in seconds, so we'll do seconds. There, you could technically pick any measure of time you wanted. You could do it in hours, but that just makes life hard. So we're going to do it in seconds through there. And then here's our number of vehicles. So again, very similar to how we set up the graphs when we were doing delay and traffic flow theory. All right, 60-second cycle lengths, that's how long our cycle is. We've got 25 seconds of effective red, and so we're going to start our graph there. And then we've got 35 seconds of green. So each one of these red bars is going to be 25. Each one of these green bars is going to be 35. They add up to be 60, right? And we know at the beginning of the cycle, at the beginning of an effective red cycle, there were 6 vehicles in the queue. So we're going to plot that over here. So there's our 6, right? And we know what they arrive. We know what their arrival rate is. Their arrival rate is that they arrive, 15 new vehicles arrive every cycle, right? So it was, if we did 900 vehicles per hour, that's 0.25 vehicles per second, and in 60 seconds, that's 15 vehicles have arrived. So that's our constant arrival rate. You can say the slope of this is 900, or you could say that each cycle you get 15 new vehicles arriving through there, right? So that's our arrival rate. We knew we started at 6 through there. And so we've got our slope. We can calculate what the slope is, right? And so in this case, our slope here is 0.25 going up through that. And then we could write an equation for this, right? So here's our mx plus b, and our b is our intercept, which is 6, right? So we've got that. So this is the equation of that line, if we want. And the reason we want to know what the equation is because we have to solve, 2 equations and find out where they're equal eventually. Right through there. We're going to do it more graphically to start with, right? So this blue line now is the cars are waiting. This is the departure side of the equation, right? And they can leave at 1,800 vehicles per hour. So this slope should be twice as steep as that slope. That's what we're saying through here. And theoretically, we can get 17 and a half cars through, right? And on that green, but they didn't all get through, right? There's this gap here still. And so that's how many cars would theoretically be in the queue when we're done. We can write an equation for this line, and you could calculate that the slope intercept is this negative 12.5. That's where you'd cross the y-axis through there. We'd actually are using this portion of the line through that. All right, so that gives us the equation of that discharge line come through here, and that's how we end up with this equation here. This is our discharge point, right? And so up to 60 seconds, these 2 equations don't meet, right? You can't solve and find out where they cross because they don't, right? We can see that graphically, but you could also prove it using math through there. So the next cycle starts. We've got our first 25 seconds of red, then we've got our 35 seconds of green. We've got the same arrival rate. So at the end of cycle 2, we're now up to 36 seconds, 120 seconds since we started. All right. Nobody moves during red, so we hold even at 17.5. Then we shoot back up. Right, and now only one car is left who doesn't make it through on green, but it's too late. Right, the next red starts. We'll see that in a second. We can come back through. We can calculate what the equation for this portion of the line is. It has a different y-intercept because we had this long flat part where nobody moved. So even though the slopes are the same, 0.5, right, our y-intercepts are different, 12.5 to 25. Right, and you can see where that plots out down here. All right, it makes sense. These are parallel. We're just moving one down, but we didn't quite make it through. Next cycle starts. We've got same arrival rate as before, and now at the end of cycle 3, 51 cars will have passed through the intersection. Great. First 25 seconds, effective red, nobody moves, so we've got 35 seconds there. 35 vehicles that holds flat through there for the 25 seconds. Through that. So sorry guy, you almost made it, but you got stuck. All right, so then you had to wait another 25 seconds, then you get to go. And now we're back at our normal departure rate until 180. So now you can see graphically that these are going to cross, right? They are our arrival line is going to cross our departure line. That's where the queue dissipates. That's when we finally empty out all of the waiting vehicles through there, right, through that. This part also has its own line right through there, and so we can calculate the equation for this departure line segment, I guess you'd call it. Through there, it's got its own y-intercept again at 37.5 below 0 on the y-axis through that. So now we've got this equation for the arrivals, and we've got this equation for the departures. They do cross, and so you can solve those. You can set them equal, right? So at some number of vehicles, these two are going to be equal, or at some x, the two y's are going to be equal, and we can calculate that. Right? So our arrival time t is equal to the third departure equation we had at the same time t, and so we can set those two to be equal, and then we can solve for t. T in this case is going to be 174 seconds, and so we're going to be right here. So 6 seconds before the end of the green, we finally clear out the queue. That's what that's telling us through that. And how many cars got through, right? So now you can plug in for the arrivals with 174 seconds because that's where they crossed, right? We worked through 49.5 vehicles. Again, this is three theoretical numbers, right, through there, so we can have fractions in that. So 49.5 total vehicles, that's the Y term where they cross. So now we know at what time the queue cleared. We know how many vehicles came through that, right? And you could plug it into either equation, the arrival or the departure equation, and they do match, so that's great. If they didn't, we did something wrong, right? So they do match for that. Well, now how much delay is occurred, right? And as you remember, the area between these two curves is our delay, so we can calculate that, right? And here's the calculation for it. All right, so we first off, we take from this orange line, we go from this, we do like a trapezoid, right? So we average out the start and the end point. 49.5 is where it ended, right? 6 is where it started. Take a half of that, and then we take that total time underneath, 174 seconds. So we start out with this trapezoid, right? And so that's that whole area. Now we're the next terms. So now this is 35 seconds long. It goes from 0 to 17.5. So we're just going to carve out that triangle of time. So that's this. Then we're going to carve out this rectangle of time, which is 17.5 tall by 25 long, right? Then we carve out this next trapezoid. Then we carve out this rectangle. Then we carve out the final trapezoid right through there. So now we're left with just the area between the orange and the blue lines through that. And if we solve that, we end up with 1065.75 vehicle seconds of delay. A lot of times we show delay in vehicle minutes and occasionally vehicle hours through there. So that's how much delay, total delay we had, right? And so what's our level of service? And so in traffic signals, we look at it as what's the delay per vehicle. And so what's the average delay? How long does the average person have to wait at this signal through there? If it's less than 10 seconds, then you're a level service A. If it's 10 to 20 seconds, you're level service B. C gets to be a bit wider range. You're 20 to 35 seconds. D is even wider than that. F is finally more than 80 seconds of wait time. Right? If you had to wait a minute and 20 seconds to get the green light, or more than a minute and 20 seconds, that's going to be a level service F. You would not be happy, right? It's not a good signal if you have to wait that long. So if we take our total vehicle seconds of delay by how many total vehicles went through, that'll give us 21.53 average seconds of vehicle delay. Where does 21.53 fit in? Right, it's going to fit into level service C. And so that's our level service C in this case, right, through there. So that's how we calculate levels of service at a traffic signal through that. It's really, we have a program that does all this for us, either Synchro or Vistro, which is what we'll use in the traffic engineering class next fall. Through that, they calculate all that for you. Right, and go through this, but this is what's based on. So now you can see how it goes. And it's going to be a little bit different if you have actuated control as your traffic signal. If your signal is smart and doesn't always give you exactly 25 seconds of green and 35 seconds of red and so forth, it's a little bit different through there. All right. And next time we will continue on with some more signal stuff.